All right, folks, I think it's that time. Welcome back. I hope everybody can see and hear me. Um, we back on the Zoom. Uh, I'm expecting no technical difficulties today. My home setup is a little more stable, I think. Um, Before we get started, I have an announcement. That is that you probably got an email concerning this, but I would like to advertise a little bit more. A voting talk. I'm giving a talk on Thursday night, 5 p.m. on Zoom. And this is one of the math colloquium talks. If you're a math major, you need to go to these. You don't have to go to all of them, but you have to go to a certain amount of them. And this is the first one of the semester. And I would suggest that you check it out. It will be fun and inspiring. And I don't know how inspiring. It'll be fun at least. And informative. This is a talk about voting and elections, the mathematics of voting and elections. It's not a talk about the election, our presidential election. Um, and it's not a talk where you will hear my opinions about politics and such. I'm happy to give my opinions about politics um, at a different venue. If you really care what I think about politics, you can ask me and I'll tell you. But this talk is not about politics. It's about voting and elections and voting in general. Um, Voting is one of those things that seems simple unless you think carefully about it. And once you do think carefully about it, you realize it's totally crazy. It's not really simple at all. So that's sort of what the talk is going to be about. I hope you'll come by. You should have got an email about it from the math department with his link to the Zoom thing. Tell your friends, tell your moms, tell your friends' moms. Anybody can come to the Zoom, and you get FYE credit. I know you guys aren't first years, but if you have buddies who are into the FYE credit, you get FYE credit. Are there any questions about that? Anybody got any questions? Nope. All right, great. Let's get down to business then. So we're going to do some more examples. Today's really going to be all examples. Examples concerning the definition of a limit that we talked about last time. I will refresh our memory. The definition of the limit of a function. So it says lim x goes to c of f of x equals L. This means trying to write the word means here. For all epsilon greater than 0, there exists delta greater than 0 such that 0 less than x minus c less than delta implies f of x minus L less than epsilon. All right. The very, very simple translation of this is something like here. This means if x is really close to c, then this part means f of x is really close to L. All right, that's how you should think of those things, although actually you should not really think of them, maybe. You can think of it that way. Those words really close are not really, they don't really have a technical meaning, which is why this weird definition with the epsilons and the deltas is necessary. All right. That's the definition we talked about last time. Today, I just want to do a bunch of examples. We did a couple of simple examples at the end last time. Maybe we'll do one more simple one, and then I want to talk about some, less simple ones. So here is another fairly simple example. Let's show that lim x goes to 2 of 5x plus 7. Find the limit and then prove it. Prove that the limit actually is what you say it is. First of all, find the limit. Anybody, any masters from calculus want to shout out? What's the limit of this? I heard somebody say 17. I agree. Remember, in a simple function like this, 5x plus 7, you can just sort of plug the value in, plug the x value in. If I plug in 2 for x, I get 17. That actually is the true answer. Let's see if we can do this. So here's the proof then. You begin by saying something like, let epsilon greater than 0 be given. You have to begin in this way. I'm going to say we will find delta greater than 0 such that 0 less than x minus 2. So I'm filling into I'm sort of plugging in stuff to the definition at this point. In the definition, what was playing the role of c, in our case, is the number 2. And the number L is 17 in our case, and f of x is the function. So over here it's going to say 5x plus 7 minus L, which is 17, less than epsilon. All right. And now, sort of our work on the side, maybe I'll do this in blue, is going to be simplifying that stuff that's by the epsilon over there. So I begin with 5x plus 7 minus 17. What can you do to simplify that? Well, in this case, you can add the 7 and the 17. I get 5x minus 10. And then this I can factor 5 out of. And as if by some magic, this x minus 2 is what I want to see from over there, x minus 2, right? This is an easy example because you don't have to do any other funny business. You just immediately see x minus 2 there. And so I can say something like, we want absolute value, 5 absolute value x minus 2 to be less than epsilon, which is the same as x minus 2 less than epsilon over 5. And so I can say let delta be, well, this is what I'm going to use for my delta, right? This is all my work on the side. Once you figure all that out, I'm ready to resume my real proof. I'm going to say let delta be epsilon over 5. And then let this business 0 less than epsilon minus 2 less than delta. And then we have, I got to show that that other thing is indeed less than epsilon. 5x plus 7 minus 17. This I simplify. I get 5 times absolute value x minus 2, right? Using the same steps that I wrote in blue. And then x minus 2, I just said let x minus 2 absolute value be less than delta. So this is less than 5 delta. But I began by saying let delta equal epsilon over 5. So that is 5 times epsilon over 5. And this is epsilon as desired. So absolute value 5x plus 7 minus 17 is indeed less than epsilon. That's that. This is how we do it. All right. This is what I would consider an easy one because, like I said, you don't need any really weird tricks inside the blue zone right there. Are there any questions about that? Because the ones we're going to do in a moment are a little more complicated. Okay, what about weird sort of cute tricks inside the blue zone? Sometimes you need to do a little something extra. Let me just say, inside the blue zone there, I'm going to try and keep that on there so you can still see it. Inside, when you're doing that sort of work on the side, this part, we simplify. Here's where the special tricks come in. We simplify, of course, using the equal sign, which is what I did here. I have equal signs here and here, right? But I would like to point out, you can also, it will still work, like your proof will still work if you use less than signs in there. That's because, notice, where did we use all of this blue stuff here? It came into play right there, right? The blue stuff was what I was doing when I did this, this simplification right here. And I would invite you to consider, what if instead of equal signs throughout here, I had used a less than sign? And the answer is, everything would still be fine down here. If I write here, instead of an equal sign, if that were a less than sign, this whole argument would still work, right? It would not mess up the flow of the logic here. Okay, so inside this blue zone, the work that you do on the side, you should simplify Usually you're going to use the equal sign every time, but if you want to, and you will see in a moment why you want to sometimes, you can use the less than sign, all right? And let me just say parenthetically, don't use the greater than sign because that really would mess it up. Then when I go to plug in the blue stuff here, it would change that into one of these, which is the wrong direction now, right? This is no good right there. You don't want a greater than sign. A less than sign would be okay, because then this entire line here would be using less than or equals. That's fine. But if you use a greater than and then later on use a less than, you got nothing. That's not helpful at all. All right, this is the moral of the story. When you are simplifying things on the sidebar, you can use less thans if you want to. And there are times when, believe me, you want to. Let's do another example. Here's an example where we have to do some extra little trick. And this is not, oops, this is not a super weird example either. Actually, if you just sort of choose a function, you know, an ordinary function, you usually have to do some extra tricks of the type that we're about to see in this example. How about limit x goes to 3 of x squared? What's that going to be? Somebody shout it out. 9. Yes, thank you. This is not a trick question. 3 squared is 9. So the limit of x squared as x goes to 3 is 9. Okay, let's just begin in the way we always do. I'm not going to do anything weird until it's called for. Let epsilon greater than 0 be given. And then we'll find delta greater than 0 such that, okay, I need 0 less than x minus 3 less than delta implies x squared minus 9 less than epsilon. All right, now I begin my blue zone here. I have to start with this, x squared minus 9, trying to simplify and somehow, remember our goal is to somehow, I'll put this like in quotes, solve for, in this case, x minus 3 in absolute value. You want to take this thing and somehow extract one of those from it. Anybody have a suggestion as far as how we could get to that? Oh, I meant to write blue in here. Anybody got a suggestion? How can I find x minus 3 in there? In the previous example, of course, all we did was factor out a constant. That was much easier. But here, what do you think? Someone said take the square root. I'm not sure exactly what you mean.
Can you factor it so that it's x minus 3?
Yes, I want to hear the F word. You should try and factor that. Maybe that's what you meant, whoever said square root. Yeah, this should become, so it's still in an absolute value, but it's x plus 3 and x minus 3, right? Factor that. Okay. Really what I want to see is absolute value x minus 3, but for that we can just do this. Remember, this is a rule with absolute values. If you have a product inside the absolute value, you can break it up into a product of the two absolute values, all right? And I like this. So I like x minus 3 here. This is kind of what I want to see here. Unfortunately, it is encumbered by this business, x plus 3. What am I supposed to do with x plus 3? It's different from x minus 3, right? The way you should think of all of this is when I say x minus 3 less than delta, you imagine delta is some very small number. And so I imagine that x is something very close to 3, right? Because the distance from x to 3 is within delta. So here's sort of my thought process at this point. X is close to 3. So what can I say about absolute value x plus 3? Whatever that is, sorry, I'm hidden there. X is close to 3. Then absolute value x plus 3 should be like close to 6, shouldn't it? I mean, yes, it should. This is the basic idea of what I'm going to do. My intention is right here. I'm basically going to replace that by a 6 or something like a 6. Now, you can't actually replace it by a 6. The thing is, I said x is close to 3, we don't really know how close it is to 3. We know it's within delta, but this delta has no specific value. This delta is any positive number. So here's the trick. We're going to say something like this. If delta is less than 1, we imagine delta is some really small number. So we might as well imagine that it's less than 1. Then what we have here is x minus 3. So x is very close to 3, right? This is 3. If x, I'm saying just imagine that x is within 1 of 3. You know, x is in there somewhere. If the delta is less than 1, then what's the biggest possible value that x could be? What do you say? Yeah, I would say 7, right? If x is within 1 of 3, sorry, 7 is not exactly my answer to this question. Then if x is within 1 of 3, then x itself must be less than 4, right? And so this is, he was answering this other question. So absolute value of x plus 3 is less than 7, right? Because x is less than 4. And so when you add 3, it's less than 7. And when you take the absolute value, it doesn't matter. It's going to be positive anyway. So the absolute value in this moment doesn't really matter. All right. And so we can continue this line here. I can say less than 7 times x minus 3. All right. I don't know if you were expecting me to put a 6 here. I said over here, if x is close to 3, then x plus 3 is close to 6, and that's true. But you have to say somehow specifically how close are you talking about? And you might as well, I just said, how about within 1? This 1 here was really my choice, but you could have picked anything, any just sort of fairly small number, and the same reasoning would work. All right. Anyway, you will notice I used a less than sign here, right? I said before, sometimes you want to use equal signs. Sometimes you have to do some weird trick where you use a less than sign. And this is that trick. And this trick you're going to be using all the time when you do examples like this. Okay? Anyway, let's continue. We're not ready to return to the main body of the proof yet, but I can continue with this part. I'm going to say something like we need 7 absolute value x minus 3 to be less than epsilon, right? And so I can, as usual, solve for the x minus 3. So we want absolute value x minus 3 less than epsilon over 7. And that's what we use for the delta, more or less. So this trick, when you do this kind of trick, there's also a sort of a weird thing you have to do when you continue the real proof. So this is all the side work, right? Now when I continue the real proof, we always begin by saying what delta is. Now, we basically want delta to be epsilon over 7. Oops. This is what we want delta to be. But in order for that to work, it also must be true that delta is less than 1, right? Because this reasoning that I used in here is based on the assumption that delta is less than 1. So in fact, we need delta, we want it to be epsilon over 7, but we also need to make sure that it is less than 1. And the way that we write that is we let delta be min of 1 and epsilon over 7, all right? This means delta is basically epsilon over 7, but we also are making sure that delta is going to be less than or equal to 1, all right? In fact, these things that I did, I was using less thans on the side work, but I think it's a little clearer if I use less or equal. Doesn't really matter. Less or equals, whatever. All right. So this ensures this min business. This is just to be sure delta is less than or equal to 1, because the argument that we used inside the blue zone there requires that delta is less than or equal to 1. And so we make delta be less than epsilon over 7, and also less than or equal to 1. All right. Now we continue. We can finish the proof. So I'm going to have you guys try one like that in a moment, but let's see if we can finish off the proof. Then we write down stuff as we usually do. So I'm going to say let 0 less than x minus 3 less than delta. And we have, remember I begin with the other part. X squared minus 9 is what I start with, right? Okay, now this equals absolute value x plus 3, absolute value x minus 3, right? But that is less than or equal to, absolute value of x plus 3 is less than or equal to 7. And absolute value x plus 3, sorry, I said that both times. Absolute value x minus 3 is less than or equal to delta, right? So here I replaced the x plus 3 by 7. That's because delta is less than 1. And I replace the x minus 3 with a delta. Just because right here we said x minus 3 less than delta. All right. And now we can continue as usual. Delta is the minimum of 1 and epsilon over 7. That means delta itself is less than or equal to epsilon over 7. So this is 7 times epsilon over 7. I replace delta by epsilon over 7. That's because delta is whichever is smaller, 1 or epsilon over 7. So either it equals epsilon over 7 or it is smaller. All right? And then this is epsilon, and that's the end of the proof. All right? So x squared minus 9 less than or equal to epsilon as desired. I said less than or equal. Should it be less than, strictly less than? This is a picky point. I don't actually care about that. It doesn't matter if it's less than or equal or strictly less than. All right. Any thoughts about this one? What are your questions about this one? This one's a little bit weirder, but we're going to try some more just like that. All right. I want to do one more like that, and then I got some for you guys to try. I'm going to see if we can do the old breakout rooms. Everybody loves the breakout rooms, right? Here is one more example for me to do. Limit x goes to 1, 5 plus x over x. Can somebody say what's the limit here? Six? Yeah, I think it's 6. If you plug x equals 1 in here, you get 5 plus 1 on top divided by 1. That would be 6. So yeah, I agree. 6. All right. Let's see if we can do it. So I begin as always. We'll find delta such that. Okay, 0 less than, here, x minus 1 less than delta implies 5 plus x over x minus 6 less than epsilon. Okay. Let's see if we can do this. So on my side, I start with this, 5 plus x over x minus 6. Any thoughts about that? How can we simplify this? Do some algebra, perhaps? What do you want to do there? What do you like? Say that again? I couldn't hear you. Right, multiply and divide a x on the 6. Maybe like trying to combine those two things with a common denominator of x. So this, I would say 5 plus x over x minus 6x over x, right? This is so that I can add the fractions. What do we get? We get 5 plus x minus 6x over x. Okay, and then you can combine the x's, right? 5 minus 5x over x. What I would like to see, remember, is this, x minus 1. What do you think? can we perhaps extract a x minus 1 from that, and maybe we'll have some other stuff left over, but
You can factor out -5.
yeah, factor out -5, okay? This equals -5, and then what remains is -1 minus or plus x, right? Like that. That actually comes all the way out as a 5, and then it's going to say x minus 1 over x. It became a +5 because I pushed it outside the absolute value sign. So the absolute value of -5 is +5. And then maybe I'll write it as 5 times absolute value x minus 1 times 1 over absolute value x. I just separate out the numerator and the denominator. All right. Okay, what can we do with this? Now, when you look at this, I look at this and I'm happy about that part, right? I like to see absolute value x minus 1. I don't feel like I need to change that around. Actually, the 5 also, I feel pretty good about, because when it comes down to it, I'm going to say like something less than epsilon, and I can just divide the 5 onto the other side. So the 5 also should not concern you. It's this part here which you should be slightly concerned about. It's not a disaster, but you need to think a little bit about this part, 1 over absolute value x. I'm going to try and do the same trick as I did last time, which is to say choose a particular value for delta, and then say this part, 1 over x, can't be bigger than some specific thing. Like in the previous example, I was able to show that this or that part can't be more, is less than 7, right? I would like to replace that 1 over x with some specific number that it can't be bigger than. So my thought, you know, the way that I would like to think about this is, let's say I have 1 is here, right? And x, well, x is nearby, close to 1, right? Then that means 1 over x can't be too big, can it? Of course, 1 over x is kind of like infinite if x was 0, but you know, 0 is not all that close to 1. So I'm going to choose my delta to make this neighborhood small enough to exclude the 0. So maybe I'll say let delta be less than a half, right? I chose that specifically to exclude 0 from that neighborhood, because the thing, the frowny face over here, that thing looks like 1 over x, and I definitely do not want x to be 0, because then that will become like infinitely large, right?
Professor,
Yes?
your head is covering some of the drawing.
Oh,
I can't see.
yeah, sorry about that.
Thank
My big head.
you.
My shirt kind of matches the blue today, doesn't it? Yeah. Yes, it does. Okay, so I chose the delta to exclude the x being 0. When x is within a half of 1, then what can I say about 1 over x? I want to say 1 over x is less than something or other. Anybody think this through? What if, so on my picture, I drew it actually going, this neighborhood actually goes all the way over to 1/2. Let me try and make this a little more accurate. Right? So x is in this range. And I want to say this thing, 1 over absolute value. The absolute value really doesn't matter at this point, because x is guaranteed to be positive if it's in that range. What would you say? Can you give me an upper bound, some value, specific number, which 1 over x is less than? I think 2, right? The biggest value that 1 over x could be when x is in this neighborhood is 2. If you prefer the, well, it's 2, right? If you want, you could say something like 1 over x is less than 1 over 1/2, because that's the smallest the denominator could be. which means that's the biggest possible value of the fraction, which would be 2 anyway. All right? And so, since 1 over x now has an upper bound of 2, we can go back here and say this is 5, sorry, not with an equal sign though, with a less than sign. This is less than 5 times absolute value x minus 1 times 2, right? And now we just have a constant and the x minus 1, which is what we like to see. This, of course, is the same as 10 times absolute value x minus 1. All right? And we want this to be, we want 10 absolute value x minus 1 to be less than epsilon, which is the same as x minus 1 less than epsilon over 10. All right? And so this is our choice for delta. So we use, to make the delta, we use this and also that. Don't forget about that. We're going to have to do one of these. Delta is the minimum of whatever, right? Everybody good so far? This is a little tricky, a little strange, I would say. But I think we're ready to continue the proof. So all of that was the sidebar. Let's continue the proof by saying what delta is. I'm going to say let delta be the minimum of either 1/2 or epsilon over 10, right? And then we will say the usual conclusion. So then I'll say let 0 less than absolute value x minus 1 less than delta. And then we have, I begin with this business, 5 plus x over x minus 6, which is what we started with. This is actually equal to 5 times x minus 1 times 1 over absolute value x. But those things, this is 5, sorry, not with the equal sign anymore, but with a less than sign. 5 delta, and I said before 1 over x is less than 2, like that, right? And then this is less than or equal to 10 times delta. Delta is less than epsilon over 10, and so this is epsilon. All right. These are a little tricky, and I think really you just have to try a bunch of them till it gets settled in your brain. Any questions about that for now?
Can you just explain again why you let delta equal less than 1/2?
Yeah. So yeah, this is the tricky part. I wanted, in this case, maybe I'll draw this picture again, fresh. So the way you want to think about this is x was really close to 1, where this distance here is delta, because that's what this means here. Distance from x to 1 is less than delta, and so delta is x is in there, right? Somewhere in that little neighborhood of 1. This means that 1 over x will be bounded. Like, the only way that this could not be bounded is if x was approaching 0. But if x is really close to 1, it will not be approaching 0. Now, you have to be specific about how close to 1 it is. And so, 0 is over here. You can really choose any value that you want for delta, as long as it's small enough to cut 0 out of this neighborhood, right? You have to choose delta just to ensure that this little neighborhood here excludes 0 over here. And so I picked 1/2, which is good enough. Although you could have chosen, 1/4 or 0.01 if you wanted to. It's just to make sure that 1 over x will be bounded. So, for instance, in some sort of parallel life, if we chose, say, delta less than 1/5, then I would have said 1 over x is less than 5, and then the rest of the proof would have worked using 5 in place of this 2. All right. Can you see the yellow? I don't know. It doesn't look very easy to see. Sorry about that. But yeah, so this is why the specific choice of 1/2 doesn't really matter, but you have to choose something, I suppose, less than 1 in this example. You need to just make it so the x can't approach 0. Right?
Thank you.
All right. Okay, let's do some examples. I want you guys to try some. We got 15 minutes left. Here are 2 examples for all the y'alls to try. Maybe I'm going to see if I can leave that on the screen. Can you even read that? I don't know. Just in case you can, I'll leave it on there. So here's 2 examples for all y'all. I would like to try lim x goes to 3 of 3 over x equals 1. And lim x goes to 2 of x squared equals 4. These are pretty similar to the ones that we just did. All right, and I'm going to make some rooms. We got room on the broom. So let's make all right, I think we're all back. Let's talk about these. I know that I didn't give you, probably didn't give you enough time to do both of them, but we got to go in 5 minutes. So would you mind if we just do the blue part for these ones? If you were writing out your proofs, on the homework or something, I would want you to write it all out, but just in the interest of time. How about the first one? You need something like, well, you should have begun with something like 3 over x minus 1, right? And you want to somehow extract a x minus 3 from that, or the absolute value of x minus 3. How did you make that happen? Anybody get this one going?
You can multiply the 1 by x over x.
Mm-hmm.
3 minus x over x.
Yes, right. So you, in order to sort of subtract the fractions with a common denominator, you do like that. And then this is, she said 3 minus x over x, like so. Right? And then this is a lot like the one that I did before. You can sort of pull a minus 1 out, or this really is, I mean, you can just do that, right? Since it's inside absolute values, you can just flip the sign of the numerator and it doesn't matter. So this is x minus 3 over x. And then I would write this as x minus 3. Just separate them out because the x minus 3 part, I like the way that is as is. I like that just the way it is. And then the 1 over x, I need to do some funny business with. But this one, is going to look pretty similar to that other one we did. The picture you should have in mind is x is very close to 3 here. And then, 0 is all the way over there. So when I consider 1 over x, I just need to make the x close enough to 3. What did you do for this one? Did you say something like I did in my example? I hear something, but I don't know if it's for me or not. Okay, so you said let delta be less than 1. Okay. You didn't do a half like I did. It's actually, in this case, there's no reason to use a half. You need to make it small enough, only small enough to exclude 0 from this interval here. So you don't have to use a half. Less than 1 is good enough. And then you can say 1 over absolute value x will be less than, what did you say for that? One half. Yes, right. If delta is less than 1, that means that this range here would be from 2 up to 4, I guess, right? And then when I go 1 over that stuff, the biggest that it could be is 1/2. All right. And so then we can sort of finish the proof off. We need absolute value x minus 3 times 1/2 to be less than epsilon. And so we use epsilon over 2 like that. Not epsilon over 2, epsilon times 2. Sorry. 2 epsilon. All right. So the beginning of the proof, which I'm not going to write just because we've only got 2 more minutes, I would begin by saying let delta be the minimum of 1 and 2 epsilon, right? The 1 from here and the 2 epsilon from here. And then all the usual stuff that we write at the end. All right. Any questions about that one? I hope that worked okay for you. You're going to have plenty of chance to do this on the homework next week. Sorry the homework this week was so short. All right. Okay, and next up was that last one I said x squared. The limit of x squared is 4. So limit as x goes to 2, x squared equals 4. I don't know if you got this far, but we got 1 minute. Let's see if we can say something about this. When it comes down to the stuff on the side, it's going to say like that, the absolute value of x squared minus 4. What can I do with this? Nobody's. Yeah, factor it. Thank you. Change it to x minus 2 and x plus 2, right? And now x being close to 2, you want to do another one of these tricks. Like this one, I like that one, right? This one, I do not like that one. The x minus 2 is what I want to see eventually in there. The x plus 2, I need to replace by some upper bound, right? I want to do less than, and then put a specific number right there, right? What's that specific number going to be? You think about, okay, what if I have x is close to 2, right? What's the biggest number that x plus 2 could be? Something like 4, although it could be a little bit bigger depending on what this distance here is. Here we might as well say let delta be less than 1, and then absolute value x plus 2 will be less than 5, won't it? If x is within 1 of the number 2, then x plus 2 has to be less than 5. And so down over here, it goes a 5 right there. All right? The x minus 2 stays like it is. The x plus 2 is less than 5. And so then I'm going to end up saying something like x minus 2 less than epsilon over 5. Sorry, I know it's time to go. I'm just going to try and write down. Sorry, I'm getting my dings here. I can't turn off my ding sound without turning off the zoom sound also. And then, so my real argument at the end will say something like let delta be the minimum of 1 and epsilon over 5, right? From there and there. Sorry, my beautiful face covering the picture again. All right, I think that's it. I went over by a minute. I will see you tomorrow.